here's an example of what happens in practice. So we're taking the word fish, and we're looking for the words that are most associated with the word fish in a large collection of news stories. So that's a track collection. So what you have here is, I'm guessing, 15 or 20 words with the highest similarity measures, with the highest strength of association to the word fish. And as you look at them, you see that they're actually producing quite different results. Right? And some of these results are a lot more useful than others. Right? So for example, fish, according to IMIM, it's associated with water. Right? They're not synonyms, but the association is good. Right? Species, wildlife, fishery, sea, fisherman, boat, all of these are related terms. Not synonyms at all, but related terms, and you may want to match on those terms. If you use something like that, though, you get a lot of words that seem just weird, just bizarre. Right? Longfin is certainly, I mean, that's longfin tuna. That's certainly a fish. But what are all these other words? Question.
So for this to work, you have to compare every token.
So the question is, for this to work, you have to compare every word against every other word. Yes, that is true. It's a bit too expensive, but if you compare it to the cost of developing a manual thesaurus, it's cheap. What you're talking about is you're talking about a good computer running for a couple months, as opposed to a linguist getting a salary for 5 years. So it's really not expensive. And if with the data structures that we talk about in this course, you can do this sort of thing on web scale in hours with the right data structure and with the right hardware. So it's really not expensive. Okay, so we get fairly weird synonyms, and some of them seem a lot more useful than others. And you can actually, if you think about it hard enough, you can actually see what's going on, and you can get an idea for what's happening, right? So the MIM here, which was the likelihood ratio test, that's the formula, right? So now look at this and think about what is the highest possible value that this quantity can take. And what I mean is, so suppose you have, what does this measure? This measures co-occurrence of words, correlation of words. So suppose I have two words that are perfectly correlated. Perfectly correlated means anytime you see A, you also see B. Okay? So what that means is N of A is the same thing as N of B and the same thing as N of AB. They all occur together, always. Now, so it's biggest when they always occur together, but once all of these terms are the same, you can actually cancel two of them, right? So maybe I can take N of AB and cancel it with N of B, and I'm just left with 1 over N of A. Now, once you see that, what kind of words will be favored by this formula? Good guess, but it's actually no.
Very rare words.
Extremely rare words. So if a word occurs once, if you have a typo, that N of A will be 1. So basically what this formula will favor, it will favor two typos co-occurring together in one document. So not extremely useful. And part of the problem there is the likelihood ratio test wasn't designed for cases where things can occur once. And in text, you have things occurring once all the time. In fact, you have Zipf's law that says that half of all the things that you ever see will only occur once. Right? So text is very different from other domains for statistics. That's why it's ill-suited to some really standard statistical tests. That's why you have to get creative in some parts of it, right? So basically, it's the typos. That's what it's selecting. It's selecting words that by chance happen to occur only in those documents where a fish occurs. And fish is not a rare word, but it still screws up the overall formula. And chi-squared actually suffers from the same problem for very much similar reasons. It wasn't designed for these extreme occurrence patterns that you see with text. Emim or dice are actually quite reasonable